Alright, what's poppin', guys? So welcome back. So today we're doing question 141, a linked list cycle. So given the head of a linked list, we want to determine if the linked list has a cycle in it. So there's a cycle in a linked list if there's some node in the list that can be reached again by continuously following the next pointer. So internally, POS position is used to denote the index of the node that the tail's next pointer is connected to, and note that position is not passed as a parameter. So I want to return true if there's a cycle in the linked list, otherwise return false. So that's a pretty lengthy description for quite a simple discussion. So all we're checking is, let's say we have a linked list, right? So if you keep traversing it, so if you keep going to the next pointer, so from 3 to 2 to 0 to -4, we can see that at the end of this -4, it loops back to one of the previous nodes. So if you keep following it, right, we can see that there's a cycle, there's a loop here, there's an infinite loop, right? So you can ever escape, you cannot ever get to an end within this linked list, right? So that's why we return true, right? And the same comes for this linked list, right? So you have this 1, you go to 2, and then the 2 comes back to 1. So you can see there's a cycle here. And then so there's a cycle within it, and if in the case if there's just 1, right, obviously there's no cycle because after this 1, it just ends, right? So how do we actually solve this problem? So we can use this by using a slow and fast pointer, right? So how we do this is we're gonna have a slow pointer pointing at the first node, and we're gonna have the fast pointer pointing at the first node also. So the fast pointer is gonna traverse 2 times faster than the slow pointer. So wherever the slow pointer traverses by go ahead by 1, the fast pointer is gonna go ahead by 2. And if there's ever a cycle in the linked list, they're gonna meet. So let's look at what I mean. So the fast pointer is gonna traverse 2 steps for every step the slow pointer goes. So the slow pointer is gonna move 1 step, and the fast pointer is gonna go 2 steps. Okay, so they haven't met yet. So the slow pointer is gonna move 1 step ahead again, and now the fast pointer is gonna move 2 steps ahead. So 1, and then because this 4, right, it comes back to 2, right? So because you can see that if we do head.next, it comes back to this 2. So now the slow pointer is gonna go 1 step ahead, and now we can see the fast pointer comes back and meet it again. So if it ever meets again, other than the first time, right, we are ensured that there's a cycle within the loop, right? So if there's no cycle, right, if there's no cycle, we can see that. Let's go back to the original position. So let's imagine that this link doesn't exist. So after -4, this -4 will point to nothing, will point to null. So this -4 is the actual end. So if there's no cycle, we can see that if the slow moves by 1, the fast moves by 2, 1, 2, the slow moves by 1 again, and the fast pointer moves by 2, 1, 2. And then the moment that the fast points to a null node, that means it has reached the end. So if it has reached the end, we now know that this linked list has an end. So that's how we do it. So this algorithm is actually called the Floyd's turtle and hare algorithm, right? So I'm gonna be explaining why this algorithm works. So finding a cycle within a linked list. So I'm also gonna explain why this algorithm is gonna run in O of n solution. So I'm gonna code it out first, and then we're gonna see the explanation later. So it's a pretty simple solution to code out once you understand how we do it. So we're gonna have the 2 pointers, right? Slow and the fast pointer. Each of them is gonna be both pointing to the head node. Okay. So we're gonna be checking the fast pointer. So while fast and fast.next, right? Because we'll be doing fast.next.next. Therefore, we need this fast.next to not be null. Okay. So while fast and fast.next, we're gonna move the slow pointer by 1 node ahead, and then we'll move the fast pointer by fast.next.next. So this moves the fast pointer 2 steps ahead. Okay. And then we're gonna check if the slow pointer equals to the fast pointer. That means they've met, right? So if they met, we know that there's a cycle within the linked list, right? So we're gonna return true, meaning there's a cycle. Then if we exit out, that means you see the fast node points to a null node. That means the fast node has reached the end of the linked list. We know that there is no cycle, and so we return false. So we can just run this and it will work. Okay, so it beats 99.39% because it runs in O of n solution. So let me explain why it runs in O of n solution. So let's say we have a cycle in the linked list. That means that we can draw it in this kind of circle cyclic graph. So you can imagine we take an arbitrary node to be the head, right? Because we know there's a cycle, right? So the head doesn't need to be the head of the original linked list. We just know that we can see that there's this cycle here. So we're gonna take one arbitrary node as a head, okay? And we now know that we can draw a circle like this because eventually one of the nodes point back to the head, right? So we denote that there are multiple nodes here in between here. So there could be like maybe 10 or 20 nodes in between here, okay? I just need to know that there's a cycle. So let's assume that there is n total nodes within this whole graph, right? So there's 1, 2, 3, 4, 5, 6, 7, and there's n total nodes, okay? So if we start at the head, right, we can see that the rest of the nodes here, excluding the head, will have n minus 1 nodes, correct? Right, we'll have n minus 1 nodes. And now let's say we have a slow and fast pointer pointing to this current head, right? If we know there's a cycle, we must know that they must meet back here. They must meet back at some location after going through the whole thing, right? So let's take the example. If the slow pointer goes by 1 and the fast pointer moves by 2, right? We now see that the difference between the slow and fast node is how many positions? 1 position off. So if we do that again, so the slow pointer moves by 1, the fast pointer moves by 2, right? We now know that the difference between the slow and fast pointer is 2. If the difference eventually becomes n, right? Because we're gonna keep traversing, right? If they keep moving, the fast pointer keep moving ahead of the slow pointer, eventually, right, the difference between the slow and fast pointer is gonna equals to n, which is the total amount of nodes within it. And if the difference equals to n, what does it mean? It means that the slow pointer and fast pointer will come back to the same node. So if we ignore this node, let's just take it as this example. We have this node here. So we have 1, 2, 3, 4, 5, 6 nodes, right? So let's move the fast pointer by 2 ahead. So 1, 2, and the slow pointer move by 1, right? And now let's move it again. So slow pointer move by 1, fast pointer moves by 2, and lastly slow pointer move by 1, and fast pointer move by 2. So we can see that it has completed one loop and it has met back here. And how many steps did it take? That took exactly n steps, n being the number of 1, 2, 3, 4, 5, right? Because if they move by n times, that means the difference between them will be n, right? The difference n, and if the difference between them is n, that means they have looped back to one cycle and they have met. And if they met, we know that there's a linked list a cycle. Therefore, this algorithm actually runs in O of n solution. Yeah. So I hope you understand that drawing. So if you enjoyed the video and found that helpful, please like, comment, and subscribe. And other than that, have a good day.